Hi everyone, I am Elif, and in this video I want to inform you about a seminar course on algebraic function fields and their applications. For this purpose, let me start with what's an algebraic function field, why we are interested in them, and what we mean by their applications. In this course, we define a function field f as a finite extension of the field of rational functions k of x, and we can come across similar definitions in algebraic number theory. For instance, when we define number fields as a finite extension of rational numbers, or in algebraic geometry, for instance, we can study elliptic curves in terms of function fields. In general, we want to study such global objects in terms of local components, such as places, and in this lecture, we will see that this notion is some sense generalization of irreducible polynomials, prime numbers, or points on a curve. Correspondingly, we will define discrete valuation rings and discrete valuation maps to be able to make computation to study their arithmetics. After these first basic notions, we will state the approximation theorem, and we will see that this theorem can be seen as a generalization of Lagrange interpolation and Chinese remainder theorem. Later on, we will focus on finitely many places that we call divisors. In particular, we will be interested in functions in a function field. They have spatial behaviors with respect to given this finitely many places. Indeed, we will see that such functions form a finite dimensional vector space, and to be able to compute their exact dimension, we will state the Riemann-Roch theorem. Furthermore, this theorem will give us important information about the global invariant of a function field in terms of their local components. So, okay, we can study the same objects in algebraic geometry or in number fields, in number theory, but why we are interested in them in terms of function fields? The first answer is that it is easy. So that means in the beginning, we want to discard complicated definitions and tools from algebraic geometry or number theory, and we want to study with these objects by the basic knowledge from algebra and linear algebra. And the second motivation is that they have nice applications. For instance, in algebraic, linear codes, in coding theory, our main object will be finite dimensional vector space over a finite field. And indeed, we will see that when we associate a vector space, such a vector space, to Riemann-Roch spaces, we can define what is called algebraic geometric codes. And the second application is motivated by cryptography, particularly two post-quantum cryptographic settings. One is code-based cryptography, and the other one is isogen-based cryptography. Here, by the post-quantum cryptography, what we mean is that it is a cryptographic protocol that has been survived so far by the attacks supported by hypothetical quantum computers. So, okay, as said before, to be able to study these objects, we need to know the definition of a vector space, what is the basis, and the definition of field, rings, and ideals. So any student who has survived from linear algebra and algebra is welcome to this course. And the structure of this course is following. So this is a seminar course. That means each week we expect from students to prepare notes and to present the idea of their notes in 90 minutes. While having these expectations, I am aware of that these two presentation skills require practice and experience. This is why, for instance, when you are working on your lecture notes, I plan to support you over an online text editor overbrief that will allow us to work collaboratively. Or, for instance, before your presentation, I try to give you some tips about teaching skills, and I try to support you how you can present the idea of your notes in 90 minutes. And the second, this is a fail or pass course. This is why I plan to evaluate you regarding your individual progress. In the meanwhile, I also plan to give you some flexibility. For instance, if you feel that you are good at programming, your assignment will be related with more computational topics. If you feel more convenient in pure mathematics, your assignment will be topics containing more abstract notions. But to be able to pass this course, you need to show up your learning progress, and I need to see. And in case of we have enough number of students, I plan to allow you working pairs, and mainly we will follow these 3 graduate textbooks. But when you look at them, if you don't find them pedagogically, that's completely fine. This is why I plan to support you by lecture notes of a lecture that I gave in the previous spring semester. So if you think that this seminar course is interesting for you, please feel free to send me an email. This is my email address, and don't hesitate to ask your questions. This is all what I want to say. Thanks for your attention, and look forward to meeting you all in the next semester.